All right, so this video we're going to do static equilibrium. Yeah, so let's define static equilibrium before we start tackling some example problems. Equilibrium, remember, so recall, equilibrium meant no net force. So the sum of the forces, vector, which is a vector, is zero. So I'm emphasizing with the vector over the zero that this is the zero vector. It means that the sum of the forces, the sum of the x components of the forces sum to zero, same with the y components, same with the z components. Static equilibrium is a little bit more stringent. Equilibrium means both equilibrium and no movement. So something sort of interesting about equilibrium, that the word without static equilibrium, is that an object can be moving. We use the word equilibrium even though the thing is moving at constant velocity. Okay, so the way you've probably used the word equilibrium outside of physics is the same thing as static equilibrium. So this is more so what you're used to when you hear the word equilibrium. In terms of equations, what this means is that static equilibrium implies a few things that are true. So some of the forces is zero. And so we're going to talk about two-dimensional problems. But you can imagine the generalization to 3 dimensions would just have some of the z components as well. But also what's new here, because there's no movement, that means no rotation. And some of the torques is zero. Okay. So these are the equations that we're going to play with for some problems today. So we can use the collection, the set of 3 equations, to solve for maybe 3 unknowns. Okay, so it's a little bit more than just f equals ma equals 0. Okay, so your book, by the way, so introduces this really quickly in the first section. Then has 3 more sections: the seesaw, a hanging sign, and a leaning ladder. So you should just think of this as 3 different examples, kind of progressing in difficulty. So I think what I'm going to do is I'll give a very simple example. We'll go over the second section. I'll just talk about it a little bit. Then we'll do this example problem, and then I'll leave sections 3 and 4 for you to review on your own from the textbook. So just to give you an idea of the sort of problems involved. Suppose you had a rod, and this is, imagine you had a bird's eye view of just like a rod on a table, or think of the rod in space even. So no mg or anything, no mg or normal force. I'm not going to worry about that. Suppose you had the following forces. Suppose something was pushing up 2f, like this, and then another force was pushing upwards right here with magnitude f. If I told you that this rod was in equilibrium and there were only 3 forces acting on it, would you know where the third force would be applied and how big it is? Okay, try and guess. You can also think of this in real life. So this thing looks like right now, without a third force, there's a net force on the rod and there's also a torque on the rod. So try and think about where if 2 people were pushing on it like this, where would the third person have to push and how strong? So it turns out the answer to this is, and we're going to develop the tools to be more systematic about this. So we definitely know it has to be a force 3F downwards. The sum of these 2 forces is 3F and upwards. So it has to be 3F and downwards, and it has to be at a particular location. And that's the new thing about this section. This is supposed to be at the end point, the 2F one. The particular location it has to be at is 1/3 the length of the rod. Okay, so whatever the length of the rod is, it has to be 1/3 the length of the rod. That has to be the position of this third force, where the third force is applied, in order for the sum of the torques to be 0 about any pivot point. So the force of magnitude 3F downwards, it could have been applied anywhere on the rod for equilibrium, for the sum of the forces to be equal to 0. But in order for both equilibrium and no movement, that requires this third condition to be true, and that requires a particular placement of where that third force needs to be. Okay, so this is the flavor of problems that we're going to do in this section. Okay, so your book talks about a seesaw, this right here. The problem is assuming that there is no mass of this rod. But the rod is important because that's the object that we're sort of summing all the torques on, that object. So like right here, even though we had no mg for the rod, we still looked at the torques for the forces that were being applied to that rod, and it was the rod that was stationary. So similar here. So it looks like your book is ignoring any mass for the rod, but there's 3 torques acting on the rod. There's M1G, M2G, and then a normal force upwards. Okay, so there's nothing interesting about forces in the x direction, so that's 11.4. 11.5 just says the sum of the forces equals 0. The sum of the force vectors is 0. So that tells you the normal force has to be equal to M1 plus M2, in parentheses G. Now, so what your book gets at is that in order for this thing to be in equilibrium, there has to be a relationship between where these two happy faces, looks like that's what the objects are, right? X1 and X2, and the two happy faces. They can't just be at any random positions and have this thing be in equilibrium. So suppose you want to know what's the relationship between X1 and X2. It kind of makes sense that the heavier thing should be a little bit closer. You probably are aware of this from experience. So we can show that to be true. So what we would do is select the pivot point. So this is section 11.2 in Shankar. So if we're wondering about X1 and X2, we're not really caring what the normal force is. So if I don't care what the normal force is, it's probably a good idea to choose my pivot point to be right here. So choose the pivot to be at the location of a spot where, if you don't know the force acting at that point and you don't care about it, that's a perfect spot to choose for your pivot point, because the normal force is not going to have a torque about that pivot point. All right. So about this pivot, these two forces need to have equal and opposite torques. Okay, so there's a F1 and there's a F2. So F1 is downward. I'm not going to write the arrow sign here. Equals M1G, and F2 equals M2G. And notice how the torques are in opposite directions. So what I mean by that is, given the pivot point, so ignore F2 for a second. Ignore F2, looking at the pivot point, F1 is going to tend to rotate the rod in the counterclockwise direction. Okay, so that's a counterclockwise torque. So tau 1 is counterclockwise. And then if we ignore this one and we just look at F2, it looks like that produces a clockwise torque. Tau 2 is clockwise. So one of them is positive, one of them is negative. It depends on which direction you call positive and which direction you call negative. Let's say that this one is the positive one and this one's the negative one. So we're going to say counterclockwise is positive. Clockwise is positive and counterclockwise is negative. So if that's the case, then tau 2 is F2 times this distance. We call this the moment arm. So it's the perpendicular distance. If you drew like a line of sight for the force, it's the minimum distance that line of force is to the pivot point. And that's called the moment arm. So this would be R2, and then this is R1. So tau 2 is equal to R2F2 and then times sine of 90 degrees. So we can leave that out, or let me just write it right down. R2F2. And then tau 1 is negative. So because tau 1, because the torque produced by force F1 is counterclockwise, and that's our negative direction, it's going to be minus R1 F1. Okay, so from static equilibrium, the sum of the torques is 0. And so that means that tau 1 plus tau 2 is equal to 0. Or it looks like, R2F2 equals R1 F1. And the x1, I don't know if your book is like talking about the x coordinate there or something, but our r's just are indicating the magnitude, the absolute value of the distance from the pivot point to that point of interest. So it's like a positive number equals a positive number for sure. So let's see what they mean by this. Okay, so right here, F1 x1 plus F2 x2 equals 0. So it looks like what they have in mind here is that the origin is chosen to be at the pivot point. So one of those x's is positive and one of them is negative. But we're saying the same physics here, in this equation and equation 11.9 in Shankar. And notice how we didn't need to know the normal force to get that relationship. Okay? The normal force didn't matter at all there. We know separately that the normal force has to be equal to the sum of these two forces for the sum of the forces in the y direction to be equal to 0. But it's the torque equation that says what the relationship of where these two objects need to be in order for static equilibrium. Okay, before we get to this problem, which is very similar to the seesaw problem, I want to talk about two facts that will help with static equilibrium problems. So I'm going to state two facts and then also prove them. Okay, so the proofs are going to rely on a little bit of vector calculus, and they're going to seem pretty boring. So maybe you just want to learn the facts and you can skip over the proofs. First fact. If the sum of the torques, so we're labeling, I'm going to use a sum, and this is just an abstract sum over however many torques there are in the problem. Like here, there are in principle 3 torques that could have appeared, but if we choose the pivot to be at the location of one of those forces, then only 2 of the torques is non-zero. So however many torques are in the problem. If the sum of the torques is 0 about one pivot point, and in addition, and also if the sum of the forces is 0, so if you already know that that's true, so if both of these conditions are true, then the sum of the torques is 0 about any pivot point. So what that means, like in this problem, is that we happen to choose the pivot point right where the fulcrum was because we didn't know, well, assuming we didn't know the normal force and we didn't need it, that the normal force wouldn't appear in our computation. But we could have chosen this point, the location of this point particle 1, we could have chosen that to be the pivot as well. That's what this fact is saying. That if you know your object is in static equilibrium, then you can choose any pivot point you want, and it'll give you the same answer. Okay, so let's prove this statement. Assuming that the pivot is at the origin, then the sum of the torques. So I wasn't writing the vector sign before, but this is so a lot of time, like all these problems we're going to be dealing with objects in the plane, and then the torque is just into or out of the screen. But this is a more general statement than that. So the sum of the torques is 0. So 0 is equal to sum of the torques is the sum of, and each torque is R, depending on where that force is, and the force is labeled F sub I. Okay. So if we change the origin of our coordinate system to R0, so R0 is going to be a constant vector. So what this means is that if the original force was at location r sub I, that force in our new coordinate system is going to be at location ri minus r naught. So for example, if we change our origin to, so look, pretend I was equal to 1. So we're looking at force F1. If originally it was at some non-zero or some location away from the origin, and we choose our origin to be exactly that same spot, then that's going to be at our new origin, if you're wondering where that minus sign came from. Okay, so so the sum of the new torques, so in other words, these are torques about the new origin. This is going to be a sum of, and every Ri is replaced with R minus R naught cross Fi. Now, the key to this proof, what lets us do this is that the cross product, like when you have a minus these two vectors, you can do R sub I cross Fi minus R naught cross Fi. Okay, so this is sum Ri cross Fi minus sum of R naught cross Fi. So these are the old torques. You know, the sum of all the torques about our old origin. And then this, you can bring the sum inside. So this R naught is a constant vector, and so you could bring the sum inside right here. And this is where we need the fact that the sum of the forces has to be 0 in order for the statement to be true. Okay, so this right here, so the sum of the forces is 0. And then this is the other condition of the problem. The sum of the torques about the old origin was 0. So this is 0. Okay. So what this is saying is that you can choose anything to be your pivot point. You know, if the sum of the torques is 0 about one thing, it's 0 about all of them. So in other words, you know, you're free to choose any point to be your pivot point, which is nice. You know, it'll depend on the problem where the best pivot point is. Basically, it's the point where you know the least about the forces acting at that point, right? Because in the torque equation they won't even appear, because if r equals 0, then it's 0 torque. Okay, so that's a very useful fact. The other fact has to do with gravity. The torque due to the gravitational force is the same as though all the mass of the object were located W-E-R-E at the center of mass. So we're going to use this fact in solving this problem. Like there's going to be a gravitational force on this rod of mass m. So the m is an extended object. Really, there's a gravitational force acting on every little piece of this. But we can just say that, you know, the net effect of gravity is just to pull down right here, mg. Okay, so this will be a very nice simplification that we can make. The proof for this one. Okay, pretend we have some extended object, and the pivot doesn't even have to be on the object. We're going to split up our mass into a bunch of pieces that have mass m sub I, and just like pivot point. And then r sub I is the location relative to the pivot point. The net gravitational torque, so the overall net gravitational torque is the sum of all the little pieces Okay, so I'm saying that we're able to split this thing up into, say, 1 million pieces, or however many you need, 1 billion, 1 trillion. You label it with I. So it's a sum of all those pieces. This is a sum of, so the torque from any one piece is R cross F. So it's R cross, and the force due to gravity on that one, on that little piece, is a little mg. So the gravitational force on the ith piece is m sub I times g. Okay, and the vector here would go on the g, not on the mass, right? Okay, so this would be m sub I times g. Okay, so I'm just going to group this a little bit differently. Right? I'm going to say the sum is on r sub I times m sub I, and then g is common to all of these pieces. Right? Now, if I multiply and divide by the total mass, let me do that here. So we have sum of r sub I, m sub I over the total mass across g. This right here is the center of mass. This is the center of mass location. So it's the total mass located at the center of mass across g is the total torque. So the net gravitational torque, adding up all the pieces, it's the same as though all the mass were located at the center of mass. This is exactly what it's supposed to be a check mark. That's exactly what the statement is. Okay, so two very useful facts that will help us with all of these torque problems. Okay, so back to our original problem. Julia is walking. Julia has mass 2m. She's walking on a uniform bar of mass m and length L, and supported on either side by two different normal forces, N1 and N2. Okay. So the way I'm going to draw this, we have a rod, we have Julia, who's at a distance x away from the left end. So now I'm going to draw, in black, I'm going to draw all of the forces on the rod. Okay, so there's a force on the rod from Julia, pushing, there's a contact force, right? The rod is holding Julia up, Julia is pushing the rod down. Okay, Newton's third law. So there's a 2m force down on the rod because of Julia. Because of this fact 2 that we just proved, there's a force on the center of the rod. So, by the way, the force pushing down on the rod is 2mg, right? If we're supporting Julia's weight. The rod has weight mg, and that acts just at the center mass of the rod. And then we have two normal forces, N2 and N1, acting on the rod. So the claim is that we have static equilibrium here. And part A, the question in part A, so these are the four forces acting on the bar. Right? I drew Julia here just as some context, but the free body diagram with these four forces are just on the rod. Okay, so keep that in mind. So I would make Julia disappear, but she's important for the definition of X, so I will not make Julia disappear. Okay, so part A asks, what is the maximum value of X so that N2 is less than or equal to mg, right? I think N2 was the one on the right, and yeah, we don't want N2 to exceed mg. And then part B just says, what is N1 at that maximum distance? Okay, so the lesson for the day is that you have some of the forces equal to 0 and some of the torques equal 0 as your equations that you can play with. Okay. So in this problem, we don't care about N1, or at least for part A, don't care about N1, and we're not asked to solve for it, right? Our condition involves N2, but it doesn't involve N1. So because of that, let's choose the left end of our bar as our pivot. Let's choose the left end as the pivot. Okay, so this is going to be our pivot point. And also, because there's two forces that are tending to rotate the rod clockwise, let's make clockwise the positive direction. And then there's only one tending to rotate counterclockwise. Okay, so also, just to make more positives than negatives, let's choose the clockwise to be our positive direction. Okay, so what we get from that is that, so sum of the torques equals 0. So what that gives us is 2mg. Now, that's not a torque, right? That's a force. That's this force. To talk about the torque, we also need the distance right there. So remember r cross f. And because they're perpendicular, we just can multiply r times f. So that distance is x. So x times 2mg. Now, the torque due to mg, due to the weight of the rod, is exactly half at the midpoint of the rod. And so for the mg force, that is located at L/2. So that's the moment arm for that one. And then minus, so those two torques were positive. They tended to rotate the rod clockwise, but N2 tends to rotate it in the counterclockwise direction. So we have minus N2L, because it's located at a whole distance L away from the left end of the rod. Those forces sum to 0. Okay, so N2, so I'm going to move N2 to one side, divide by L. Okay, so N2 looks like it's 1/2 mg plus 2mg times L over x. No, x over L, sorry. And we're going to require that is, so as the problem statement says, we want it to be less than or equal to mg. So N2 depends on where Julia is, which makes sense. So let's see where this, what this implies about the value of x. All right, so we're going to subtract 1/2 mg from both sides. 2mg x over L is less than or equal to 1/2 mg. And then divide both sides by mg, divide both sides by 2. Looks like x is less than or equal to 1/4 L. Okay, so in other words, the maximum x coordinate that Julia can have, so that the normal force N2 doesn't exceed mg, is L/4. Okay. Now, what is the, for part B asks what is the, so I'm just going to scoot this stuff up because part B is going to be real quick. It's going to be like one line. Part B asks, what's the value of N1? Well, the sum of the forces in the y direction has to equal 0. So if N2 is equal to mg, so let me draw these. So another color will probably help here. So part B asks, what is the value of N1 when N2 has this maximum value? So you have mg pointing up there. You have the contact force from Julia pushing down on the rod. That's 2mg right there. There's the weight on the rod, mg. So can you guess what this needs to be in order for static equilibrium? That's right. This needs to be 2mg. Okay. This is the answer for part B. So N1 has to equal 2mg in order for the sum of the forces in the y direction to equal 0. So you could have done part B, and you might want to double check this. You could have made a different point your pivot. So try making the right end of the rod your pivot point. So Julia is at location x equals 1/4 L, that distance away from the left end of the rod. Choose the right end to be the pivot, leave N1 as a variable, and just solve for what value N1 needs to have in order for the sum of the torques about this new pivot point to equal 0. And you should get the same answer. You should get 2mg. Okay, so this is the type of thinking that goes into all of these torques equals, sum of torques equals 0 equations. So because of this first fact, you only, so you have 3 equations to play with, basically. You can, most of the time, this is the easiest way to go forward, is to use 2 force equations, 1 torque equation. You can also replace, so this winds up being equivalent to sum of the torques about 2 different pivot points equals 0, and then you just need 1 more equation from forces. So just like with the example with Julia, we could have done 2 torque equations to get the answer. And we wouldn't need this for part B. We could have used a different torque equation with a different pivot point. Okay, so the sum of the torques just gives you more stuff to play with when you're solving static equilibrium problems. Okay, so your book goes over hanging sign. The unknowns here are the tension and the force from the wall on the hanging sign. So because we don't know either component of P, that's the natural choice for the pivot point for your sum of the torques equals 0. Okay, you choose a point where you don't know much information about the forces at that point. Okay, so they choose that to be the pivot point, do sum of the torques equals 0, and then sum of the sum of the forces x and y components equals 0. So that helps you with the hanging sign, and then leaning ladder also with friction. So the friction you can't set equal to its maximum value unless you're told to do it for some reason. So here they impose that condition. It gives a condition on the on right here on the angle. Okay, that's static equilibrium. I hope you have fun with these problems.